Okay, now let's go back once again to the tutorial we had, and what we're going to start with is going to be the let's take the springs. I'll take the springs one. So let's open the spring one. Okay, now let's spring one. Okay, so what we're going to cover in the spring one is the following. First, the objective is going to be to apply the motion simulation module on the SolidWorks Motion 2012 on the variation analysis of the single degree of freedom vibratory systems. So exercise number 1 is going to be the vibration analysis of the simple pendulums, and the exercise number 2 is going to be variation analysis of a simple spring mass system. So before we start, this asks you to download 2 zip file, the pendulum zip file and the SDOF zip file, and actually that's what we're talking about are here, these 2 files, the SDOF and the pendulum one. That's the pendulum one, the one we're going to start with at the moment. So go back once again. So before we start, once finished both, you're going to have some Excel sheet actually on the view, pendulum XL and the SDOF, because they have some analytical solutions for comparison with the solution you're going to have from the SolidWorks motion analysis. They should be almost the same, compatible between the results you're going to have on the SolidWorks and the one you are going to have on the Excel sheet. So first we are going to start with the vibration analysis of the simple pendulum. So this is a physical model of the simple pendulum system. We have the pendulum at the certain position. We have the chord length is L, the angle is theta, distance horizontally is going to be X, vertical is going to be Y from the hanging point. Position number 1, 2 and 3, and we have the mass multiplied by G, which is the 9.81, is going to be the weight of the ball. This we have here is L multiplied by 1 minus cosine theta. Okay, now that's the datum line and datum point. That's the 0 position. So simply, a simple pendulum system is typical a single degree of freedom system which composed of a sphere and rods rigidly connected to each other according to Newton's second law of motion by taking the form of summing the moment about the point O. We're going to have the moment around point O is equal to the IO multiplied by alpha, and the IO is equal to the mass multiplied by the length of the chord square. The IO multiplied by alpha as a function of time is equal to minus mg multiplied by L multiplied by sine of theta multiplied by t. And we can simply find out that sine of theta is going to be equal to, almost going to be equal to theta. Then the equation of the motion of simple pendulum can be or neglected mass of the rod, as well as the fraction of the hinge is obtained by the homogeneous second order differential equation with the constant coefficients, as we can see here. Talking about the the acceleration, and we're talking about the displacement angle. The homogeneous solution for this equation is written as theta of t is equal to the AT multiplied by cosine of omega n t plus the h2 multiplied by the sine of the omega n g, where the omega n is equal to under square root of the k divided by m, or is going to be equal to the under square root of the g divided by l. A1 and A2 are constant defined by the initial conditions of the pendulum. For the current model, the L is 100 mm, the G is equal to 9.81, and omega is going to be simply under square root of 9.81 divided by 0.1 meter, and this will be 9.903 radian per second. And the period of the vibration T is going to be equal to 2 pi divided by the omega n, and we are going to have the interval time is going to be 0.634 seconds. Apply the initial condition of theta at position 0 is equal to the A1, and theta 1 is going to be equal to minus 10 degree. Theta dot of 0 is going to be omega n multiplied by A2, and equal to 0. And we have the A1 is equal to 10 degree, A2 is equal to 0. Then the solution is going to be finalized as the following equation. So the theta t is going to be equal to minus pi over 18 cosine of 9.903 t. Also the theta dot t, the velocity, the angular velocity we're going to have, is going to be equal to, by substituting all the values of the minus theta o, omega n sine omega n t, and we're going to have that the answer is going to be equal to pi over 18 9 multiplied by 9.903 multiplied by sine of 9.903 t. And for the acceleration, we're going to have the other equation, which is going to be minus theta o omega n square multiplied by the cosine of the omega n t, and that's the answer we're going to have. So first we're going to have, for the learning CAD model of the simple pendulum system, and the exercise number 1, the assembly can be open, and we're going to have the shape you can see below. The radius of the solid sphere is going to be 10 millimeter. Okay, the radius of the sphere, which is the ball, and the length and the radius of the solid rod are going to be 90 millimeters and 0.25 millimeters. Okay, the length is 90 millimeter, and the radius is going to be 0.25 millimeters. Both the sphere and the rod are made of aluminium by specifying the aluminum alloy 2014 SI units are used. The top of the rod is going to be connected to a grounded wall with a revolute joints by 2 mates. The concentrating and the coincidence for only rotating according to the z-axis in the xy plane. The third mate is going to be the angle introduced for defining angle of displacement theta 0, which is going to be equal to minus 10 as t equal to 0, which should be suppressed during the motion analysis. Okay, so these are the mates we are going to have for us. So we have to switching for the SolidWorks Motion Manager as we learned earlier. Okay, so we go to there, we're going to have motion study, we go to have motion analysis. Now, and this time we're going to have motor, by the way. We are going to fix and moving components. As we can see, obviously we are going to once again use the fixed float status in the SolidWorks model. In our case, the ground component is going to be fixed. The ground component is going to be fixed, while the pendulum is going to be moving, floating. So that's what we are going to see here. F for the ground, and pendulum is going to be free. Double check that. F grounded, and this one is floating. So specifying the gravity is very important. Click the gravity button from the motion toolbar to activate the gravity dialog box. Choose the Y and keep the value of 9,006 millimeter per second square in it. This value. Okay, make sure that the green arrow is going to indicate the direction of the gravity to be downward, which is going to be opposite to that of the positive direction. Then click OK. So we go to the things, search for the gravity. On the previous type it was an apple. I can see an apple here. Click. Okay, so once again, let's see what he chose. Just the Y. Direction of the set is going to be downward, 9.08 gravity. So I set the gravity, I got the things to be at 5 millimeters directly. So the motion analysis type, we will choose the motion analysis because it's going to be the most sophisticated motion analysis tool, reflecting all the required analysis features such as the internal properties, the external forces, the contacts, mate fractions, and extra. For the simulation time, we set that by default we get to 5 seconds. We should take it to 1.5 seconds. Note that the angle mate should be suppressed during the motion analysis. Okay, that's the angle. Did he say? Yeah, the angle mate. This one. So first I'm going to take this one to 1.5 seconds. Should be somewhere in the middle here. Go to the mates. This one. Okay. Now, next, I have to check that this one has been suppressed as well. So go do that. Check the mates. Yes, it's suppressed. So what I'm going to choose is that the motion study properties, animation, basic motion, motion analysis. The frame per second is going to be set at 300, and the accuracy is going to be 0.0001 to be set. So actually, the properties we're getting from here. The frame per second we said is going to be 300 frame per second for the motion analysis. 300. Now in this case, this one is set already. Okay, click the motion study properties bottom for the motion bar 300 for the frame for the get smooth results. In the SolidWorks Motion Manager, click calculate. You can also increase the value for the accuracy to low height. So that's mean this one will be okay. Click that. I can see it's moving. It's on the front. So actually this one has been designed to go by 10 degree, negative 10 degree to positive 10 degree and come back. It's going to take some time to finish, so let's continue reading. Okay, now click calculation. You can also increase the value of the accuracy from low to high. I left it at low at the beginning. Running the simulation. In the simulation sphere, swinging between minus 10 degree, that's mean to the left, to positive 10 degree to the right. Then we have to looking for the results. Once again, we are going to click the result and plots and open the result dialog. Under the result, we can select the displacement, velocity, and acceleration, angular displacement, velocity, acceleration, and the magnitude respective. Click OK to show the plot, and we're going to have the following results. So let's wait for the things to finish. Yeah, now it's finished. Now, still moving? No. Okay, now we go to the result. Select this one. Sub-selection where? Angular displacement, velocity, and acceleration, and magnitude. So we are going to have for the angular velocity. That's number 1. I think I have to click the surface. Yes, yeah. I have to click the face and get the Z component, and the face of the ball will be chosen. That's the first one. Go once again, go for the other type, which is the angular displacement, I think. Angular velocity, angular displacement, and angular acceleration. got the angular displacement, yes, angular velocity, angular acceleration. Now I'll keep this one, check what we have here. So he said we're going to have the following results. Angular displacement, I got the angular velocity. So the angular displacement went up to from -10 to 10 degree per second square. For the angular velocity, I went from -99 to 99, the peak to peak. According to the 1.5 seconds. So let's check what we had as the results. Okay, so I'm going to keep them one next to each other. So that's the angular velocity from 99 to -99. Okay, so the peak was at 0.15. Is that correct? Oh, my peak. Sorry, yeah, 0.15. And for the angular displacement, we said we are going to have it from -10 to 10, and 0.3 will be the peak. The angular displacement, yes, right. And let's see if we have the angular acceleration as well. Angular acceleration, yes. So 972 to -972. Yes, and the bottom is going to be at 0.3 and so on. Okay, now we finish with this one. We are going to take these results and you're going to compare to the result we have on the Excel sheet. Now the other type is the vibration analysis of the simple spring mass system. So we have a mass, the blue box here. We're going to have a spring, and we have a certain angle for this edge. Pull the body downward, and it's going to go up once again due to the vibrating we're going to have in this spring. And simply physical mode of spring mass system. A simple spring mass system is going to be typical single degree freedom system, upward and downward, and during vibration, which is going to be composed of the mass and the spring connected to each other. The simple K and M system is going to is shown in the figure above, in which the mass M is going to be sliding along the 30-degree slope with the spring stiffness K and the free length of the L of the initial length, and connected to its top end of the slope. The mass will be slide back forth along the slope surface under the two scenarios. First, free vibration Ft is equal to 0, and B, the force vibration under the sinusoidal force Ft. The x-axis is located in the surface of the slope and originated from the top end. So the solution of free vibration of simple spring mass system, according to the second law of motion, by taking the form of summing of the forces about the x coordinates, is sigma fx is equal to the mass multiplied by g multiplied by the sine of the theta, minus k for the string multiplied by the x minus the LO, the distance we are going to have, minus the original length. This will be equal to the m multiplied by the linear acceleration. The linear x dot double dot plus k multiplied by the x minus LO is going to be equal to the mg minus multiplied by the sine of theta, and then we're going to have the mx dot double dot plus kx is going to be equal to the mg sine of theta plus k LO. Then the equation of the motion of the spring mass system, with neglecting mass of the spring as well as the friction between the contact surfaces, and the block is going and the ground is going to be obtained by non-homogeneous second order differential equation with a constant coefficient. Thus is going to be total solution of the summarization of the summation of the two parts. And so that's the equation we're going to have. Dependent, therefore, so you have to read this one, but actually now it's 11:27. I feel tired. Solution of the harmonically forced vibration of a simple spring mass system we're going to consider that the external force is applied harmonically in cosine function from the ft as equal to the fo multiplied by cosine of omega f multiplied by t according to the Newton's second law of motion. By taking the form of the summing of the forces about the x coordinates, we have that its equation of motion is going to be equal to the m dot plus kx is equal to the mg sine theta plus klo plus fo multiplied by the cosine of omega ft. Then the equation of the motion of the spring mass system with neglecting the mass of the spring, as well as the friction between the contact surface and between the block and the ground, is obtained as a non-homogeneous second order ordinary differential equation with a constant coefficient, and thus its total solution is going to be summation of the two parts. So general homogeneous solution x of ht is going to be equal to the a1 multiplied by cosine of the omega nt plus the a2 multiplied by the sine of omega nt, where the omega n is going to be equal to under square root of the k divided by m, and the a1 and a2 are constants defined by the initial conditions. The particular or special solution for the xp of t is going to be equal to the mg sine theta divided by k plus lo plus the fo divided by the k minus omega square f of m multiplied by cosine of omega ft, which is going to be dependent on the time, of course. In fact, compared to that, in the free vibration solution, there is one more harmonic term related to the external excitation force. Notice that the particular solution is going to be always determined according to the non-homogeneous term in the right side of the ODE. Therefore, the total solutions can be rewritten once again as the x as a function of t, displacement as a function of time, is equal to the a1, the constant, multiplied by cosine of omega nt, plus the a2 sine of the omega nt, plus the mg multiplied by sine of theta divided by k, plus the initial length, plus the fo divided by the k minus omega square omega f square multiplied by the m, all multiplied by the cosine of omega f t. In current analysis, the fo is going to be equal to the 10 pounds, and the omega f is going to be equal to 2 pi radian per second. Still applying the initial conditions, the x at O at time is going to be equal to the A1, which will be equal to the x initial, which is equal to 4 inches. For the x dot of t is going to be equal to 0, we have that the A1 is going to be equal to the x initial minus mg sine theta divided by k plus lo plus the fo divided by the k omega square m, and the a2 is going to be equal to 0. Then this solution is going to be finalized as the following equation. The Cad model of the simple Mendeleev system is already been given, and you can find it under the name of the SDOF SolidWorks assembly. So we are going to use the IPS units, which are going to be the inches and the pounds. So I will close this one. Don't save. I'm going to open the new one. Going to the folder, the SDOF simply. So now that the part we don't have the spring. Actually, we're going to add the spring from the SolidWorks itself. So this part can slide over the shape, and we are going to add the spring to it. So we have that. We are going to have coincidence between the ground and the block and so on. So these are the mates we have. We have to have a limit distance 1 between the faces. So just remember first that we are going to have we have to change the unit first. Edit think units can be found here. Just let me check if it's already in inches. Oh yeah, it's already defined at IPS. So okay, elastic model. We have 3 mates as shown, 2 coincidents and 1 limit distance. The block is going to be allowed to move along the slope surface only. The limit distance made between the surface of the block and the top of the surface slope is defined in neutral and the initial positions at the 3 inches, 4 inches respectively. Also that to avoid any unrealistic results, the upper and the lower limits of the distance are set at as 9 and 0 inches respectively. Because of the total length of the slope is only 10 inches. So for the limit distance, we're going to set this value to be 4 inches. Okay, we already had the main selection, so limit distance. Okay, it's already been set, so I don't think we have to do this one. Ground and the block. So once again we have some moving parts and fixed part. The floor is going to be the fixed one and the block is going to be the moving parts, specifying the gravity from the motion toolbar. So I have to check the motion toolbar. Nope. Take out this one part. Okay, so I'm going to set the gravity. Okay, we should have it this way and click OK. Now, single pole, choose this one, the gravity downward, opposite Y direction, and then click OK. Did I choose the Y direction? Actually it's on the Z direction, so I have to change that. Delete. And now it's working. Okay, we got this one, specifying the spring. Okay, now we are going to press the bottom of the string and we are going to choose between the 2 faces. And if you go here, we will find the spring. We have to define the 2 faces. It's going to be the face number 1 and face number 2. And we can see that the spring has been generated. We can change the property of the spring itself, as you can see here. 1 decay is going to be 20. The diameter is going to be 3 inches. So 1, 20, 3, 1, 20, and the 3. Okay, then we go down to here and check these values: 0.393, 0.75, 5.25, 0.75, 5.25. Okay, so we increase the thickness of the spring itself. Specifying the initial, press OK. Now we had the spring. It's non-visible, but actually does exist, and we can work on that. So specifying the initial position of the spring, we stretch the spring of the block. Stretch the spring with 1 inch downward along the slope surface as the initial position of the block. Then the block is going to release for the free vibration scenario. we edit the mates of the limit distance. In the 4 for the distance dimensions, know that this type of mate can be kept during the motion analysis. So limit distance. So let me check how to get the limit distance. Okay, so that's what I'm going to have for limit distance, and he asked us to change this one to 4 inches. Okay, let's see what he changed as well. Nine as well. Okay, 9 4 inches. Okay, now motion analysis type. Motion analysis, we still choose the motion analysis because most specified one, the time is going to be 5 seconds. We have to take it to 0.25 seconds only. This one 1.5.2. Okay, we change the time, simulation of the free time. Okay, now motion analysis type. I choose this one, external forces, 5.45 seconds. Okay, and light camera, running simulation, and let's see what will happen. Okay, speed will be set 5 seconds per flow. So you can see that the block and the spring are vibrating upward and downward in the time of the 0.25 seconds. The interval of doing that is going to be 5 seconds. So keep this one moving. Let's go and read what's going on next. Looking at the result of the free vibration, we have to go to result and plot. Click this one, choose the displacement and acceleration. I'm going to choose the linear displacement and the magnitude. And then we're going to have showing the results of the phase 1 and ground phase 2. Okay, so we go to the results, select displacement, select the linear displacement, and for the 2 points of the faces we are going to have are this one there. Okay, we have to check the magnitude here, create a new plot and time. Magnitude, press OK. So that's the first diagram. Okay, so we can see that this one is starting from 4.5 to 2.6. Let's check that. Correct. Okay, so if I'm going to choose 2 parallel edges instead of the faces, and then we will do make another one. So top of the end slope relative displacement between them. Instead, we can extract the result correctly. Okay, the 2 edges, edge 1 and edge 2. Actually I can yeah, the lower one was about 2.6, so I'm going to do that. I have to change these values. Result, plot, in features. Okay, now I got the results, the correct one. Okay, and specifying the force for the force vibration, and then I have to choose the force button for the motion toolbar to activate this dialog. Choose the linear force within action only for the direction on the end of the face of the block, as well as the force is set relative to the assembly origin. The amplitude of the force is 10 pounds and the frequency is 1 Hertz, and the average of the force is going to be 0 pound, as well as the phase shift is going to be 270 degrees to convert the sine function by default to a cosine function. Therefore the FT is going to be equal to 10 cosine 360t. Click the picture icon in the force function parameters. The sinusoidal force function will be shown for a double check. So I will choose that, force. Okay, that's your force. Okay, then start to make all the dimensions. So action only, and the face of the block number 1 is going to be chosen here. Then I'm going to leave it as space. I'm going to go to sinusoidal force 10, 1, 0, 270. Sinusoidal. It's a different thing as well. The force function. That's the force function. Okay, so step, harmonic, sigma, expression, load, function, for file, the function. Let's go for the harmonic. Oh, yeah, once again, force function, AF average, pH. You can see it's different from one version to another. Okay, it's here, it's harmonic. Harmonic 10, 1, 0 to 170. Harmonic 1, 10, 1, 270. Okay, and the force first time is going to be the new drawing, and it's from -10 to 10, and the bottom is going to be at 0.5. Where's my volt? Okay, the force, the features. Force this time. Selection of the force vibration. Now, how to get this one first? Click the graph to enlarge. I don't have any graph here. That's strange. Anyway, I'll have to accept it as it is because I don't have any graph here. So let's see the other part, which is going to be the simulation time of force vibration. So because SolidWorks set default analysis duration is 5 seconds, this parameter needs to be modified by moving the end time key to topmost line from 5 seconds to 0.5 seconds location, in which a bit longer than the free vibration. Okay, and that's what I'm going to do. Simulation of the time, force, vibration. That's left already, so click that. Something wrong. Result, reduce two parallel edges and the block tone at the end. Well, actually it didn't work for the force. I'm going to leave this one because I feel so tired today. I think I'll stop at this stage and we shall continue